let's go ahead and get started. I hope your fluids exam went well today, for those of you who took it. So homework is not due today, it's due on Thursday, that's a strict deadline. And I have already posted the next homework on Blackboard, just so you can see it and get started. Anybody who's interested in getting that done before they leave on Thanksgiving vacation, it's there for you, because you want to enjoy your vacation. There is also an additional opportunity for you to earn some extra credit. So there's a Thanksgiving extra credit assignment, and there's 3 different options for you to choose from. The first is determining the temperature and relative humidity of your kitchen before and after cooking all of the Thanksgiving meal. So presumably there's going to be a lot of moisture added to the air. It'd be an interesting experiment to figure it out before the cooking process, and then at the end of the day what it is. And then do a little write-up about that and include pictures. So when we did that in class, we used fairly simplistic setup to do that. So if you have any kind of a thermometer and any kind of a little fan, you can make a simple experiment. So whatever you choose to do, you just need to document it, tell me and explain the process, and then the results, calculate the results. Option 2 is to estimate the total time and energy it takes to cook a turkey. And I want you to figure it out doing 2 different ways. So if you smoke it or deep fry it or bake it or boil it or whatever it is, just try to determine the difference between the 2 methods. And you can go and Google how long does it take to cook a turkey, and there's a lot of information out there about how long it takes. But I don't want to necessarily know how long it takes. I want you to figure out how long it takes. So that's more important to me, is the process of you making certain assumptions about your turkey, about the temperatures, about your oven, whatever it might be. Just the process that you go through in order to determine some of those variables is what I care about, not necessarily how long it actually takes. But you can look at those answers on the internet to see if your answer is reasonable. And then if you want to compare it to how long it actually took the turkey to cook on Thanksgiving and see how close you were, that's another good thing to put in there. And then the third option is estimating the fuel consumed as you travel to your Thanksgiving destination. And I'm assuming most of you are driving. If it's air travel, it's a little bit more difficult because airplane fuel is very different, and it's not something we've studied as far as byproducts and things like that. So there's some assumptions that you need to make with that. So assuming incomplete combustion where you have 5% carbon monoxide, then show all the work, any assumptions that you make, and then if you have, again, additional data where you actually filled up your tank of gas at the beginning and you filled it up at the end, so you know exactly how much fuel you consumed. You can look at theoretical and actual values and compare some things. Okay, so this is 20 bonus homework points. It can go to just on top of your homework score. It's worth 0 points, so you just get 20 points. That can help boost your average for those of you that are interested and need it. You can do any of those 3 or all of those 3, but you only get credit for 1. So choose wisely, right? One that's interesting, and it'll be due the Tuesday after Thanksgiving. So hopefully you can have fun with that, and it can be interesting to you. Okay, so today we're continuing our discussion of combustion processes, and now we're going to talk about the first law analysis. So up to this point, we've really just been looking at mass balance of these combustion reactions, but now we're going to look at the energy balance. So in that, the primary consideration, or the primary thing that we're looking to solve or find, is how much heat is released during these reactions. And so we're going to look at it both for an open system and a closed system. And then we're also going to talk about something called an adiabatic flame temperature. So if your system is adiabatic, and there actually is no heat released to the external surroundings, what's the maximum temperature that your system can reach? So that's the adiabatic flame temperature. And there are quite a few examples today, and again, these examples are not that difficult, but you have to be very orderly and keep track of all of your numbers, right? So you may have 10 different components to your equation with different energy values. You need to be very careful when you're writing things down and not just use your calculator and get to the end and write down a number. If you write down the steps, it's a lot easier to find where you made mistakes. And I always recommend that if you are calculating these very long equations with a lot of inputs, that you do it twice. So do it once, write it down, do it twice. If you get the exact same number, that's a good indicator you probably did it right, or you made the same mistake twice. But if you get a different number, then you really need to go back and make sure that you punched everything in correctly. Because it's easy, I even did it when I was solving the homework problems, that sometimes you get to the end of it, and the number you have is a number, but you know, there's a negative sign you missed or something like that. So always do it twice, double check. Okay, so energy balance applies to reacting and non-reacting systems. Up to now, we've only really looked at non-reacting systems. So like turbines and pumps, they have energy interactions going on, but there's not chemical interactions that we were overly concerned about. Well, with combustion, that's one of the primary considerations is these chemical reactions that are ongoing in our system. So any system that has these chemical reactions is considered a reacting system. And if we're talking about energy, it's necessary for us to talk about enthalpy. And the enthalpy of a substance can be expressed in a way that we can also include this chemical reaction that's ongoing. So when we did the energy balance for a steady flow system, it's just adding up these enthalpies of the inlets times their mass flow rates and the enthalpies of the outlets times the mass flow rates, finding the difference between the two and seeing how our energy changes over time. In this case, we're doing that also, but now we're looking at these combustion reactions and the sensible energy that occurs due to these molecules changing and bonding with other molecules and moving around. So we have to account for that energy in our energy balance. And so if we were to rewrite the energy balance, it's similar to what we've seen before, where we have Q in and work in and Q out and work out. But now we have this term here. So instead of looking at the mass flow rate, we're looking at a molar flow rate in this particular term, times the enthalpy of formation plus the enthalpy of our system at the whatever state it's at, minus the enthalpy at the reference state. We'll talk about that in a minute. But we look at it in terms of the inlet conditions and the outlet conditions. But in this case, our inlet and our outlet will have reactants coming into the combustion chamber and a product leaving the combustion chamber. So reactants would not be synonymous with an inlet, but you have reactants at the inlet. And in some combustion processes, if it's a multi-stage process, your products at the outlet may also become the reactants at the inlet of another process. We're not doing any of those in this class, but it's important to distinguish the difference between inlet and reactant, that they're not exactly the same, but for our purposes with a single-stage combustion, they can be treated on the same side of the equation. We can also look at this on a per mole of fuel basis. So instead of knowing the molar flow rate, we simply need to know the number of moles of each of the reactant component. So where we have this summation term, it means that if we have multiple reactants coming into our system, let's say we have some kind of a fuel plus air plus oxygen plus whatever it is, that we have to sum them all up and look at the enthalpies of the individual components. Yeah, so these equations start getting big. Same thing for the products, that we have to look at each individual product, how many moles of that product we have at the final stage, and then the enthalpies of that individual product. So we can also rewrite it in a more simplistic form in these ways. It's important to note that for combustion processes, we generally don't have a work term. There's no mixing involved. It's just simply these chemicals coming into the system and some heat being applied or some ignition happening. And then most often it's an endothermic reaction, or an exothermic reaction, sorry. So there's a heat out term. So as these materials combust, they're ignited, there's this chemical process that occurs, then heat is released. And the purpose of combustion, why we undergo combustion, is not so we can combine these materials and get a byproduct. It's so that we can have heat for other processes. So this is like looking at the other side of the curtain from all the steady flow power plants that we looked at previously, we just simply said there was some heat in. Well, now we're figuring out how much heat in and what products are combined together in order to give us the heat that we need for our particular steady flow process. So Q out is equal to the sum of the reactants minus the sum of the products. And this equation is what we'll use for most of our examples today. So let's start with our first example. We have hydrogen in the form of H2, and it's burned completely with a stoichiometric amount of air. What does that mean, stoichiometric amount of air?
Theoretical.
Okay, it's a theoretical amount, but what is that in physical terms? What does that mean?
There's no excess.
There's no excess. Okay, so it's the right amount of air for our combustion process to happen. There's no extra air, there's no deficit of air, it's just the right amount of air, so the stoichiometric amount. If both the reactants and the products are maintained at 25 degrees Celsius and 1 atmosphere, and the water in the products exists in the liquid form, so H2O coming out is going to be a liquid, determine the heat transfer from the combustion chamber during this process. Okay, so we have hydrogen coming in, air coming in, we'll have liquid water coming out, but what else will be coming out at the outset if it's complete combustion? What are some of the other products we typically see? CO2. Okay, do we have any carbon coming into the system? No. Okay, so there's just hydrogen, oxygen, and nitrogen coming in. Ordinarily, if we were working with a hydrocarbon fuel, we would see carbon come out in the form of CO2. In this case, we don't have any, so we don't have to worry about it. Okay, so hydrogen, so water is coming out. What else will be coming out? Nitrogen. Yeah, so we'll have water and nitrogen on this side of the equation. So if we were to look at this equation, we have hydrogen plus the theoretical amount of air, it's O2 plus 3.76 N2, reacts together, and our products are going to be H2O in the liquid form plus some amount of nitrogen. Okay, so now we need to perform a molar balance on both sides of the equation to figure it out. So if we look at our hydrogen molecules, we have 1 on this side of the equation, and on the other side of the equation we have an X. So X is equal to 1, that's pretty easy. If we look at oxygen, we have A theoretical on this side of the equation, and on the other side of the equation we have X over 2, because this is monatomic oxygen, whereas this is diatomic oxygen. So the theoretical value of X over, or the theoretical value of air is going to be equal to X over 2, so it's 0.5, since X is 1. And then for nitrogen, we have 3.76 times A theoretical is equal to Y. So 3.76 times 0.5, we get 1.88. So we could rewrite this equation, replacing A theoretical with 0.5, and then over here, we replace our X with just a 1, and Y is 1.88. Okay, so far we have balanced our equation so that we have complete combustion using the theoretical amount of air. We know our reactants and we know our products. Okay, so now we perform an energy balance, and we can jump right to the equation, or we can start with the old form, Q in minus Q out plus work in minus work out. But we'll find that we end up canceling out Q in, and work out, so we just simply have a negative Q out is equal to the sum of the number of moles of the product times H sub F, that's the enthalpy of formation, plus the enthalpy of the current state minus the reference enthalpy, that's a minus the sum of the number of the reactants, enthalpy of formation, plus enthalpy minus enthalpy of the reference state. Okay, so for each one of our products and each one of our reactants, we need to go to the tables and look up some values. So we need to look up the enthalpy of formation, the enthalpy, and then the enthalpy of the reference state, which is 25 Celsius is 298 Kelvin. Okay, so if we go to table A26, we can look up some of these values. So we're going to look up for hydrogen, oxygen, nitrogen, and liquid H2O. So we're going to look up the enthalpy of formation for each of those. We're also going to look up the enthalpy at the reference state, which we don't end up using as a reactant. Okay, so in table A26, can anybody tell me what the enthalpy of formation is for hydrogen, oxygen, or nitrogen?
I got a quick question.
Yes.
You could go back a slide. Where did you get the 0.5 and the 1.88 and the 3.76?
By balancing this combustion equation? Mm-hmm. You mean how we did that?
Yeah, like how'd that come about?
Okay, so you look at both sides of the equation and you compare the number of moles of things that you have. Okay, so in this case, if I look at hydrogen, I see on this side of the equation, well, I have to rewrite this. I already have the answers, so let's write it again. So the original equation was H2 plus the theoretical amount of air times O2 plus 3.76 N2. H2O, we have some coefficient in front of that, it's in liquid form, plus Y times nitrogen. Okay, so we know what's coming into our system. We know that it's hydrogen plus the theoretical amount of air. We don't know the exact number for that yet. We have to solve for it. And then we know the byproducts are going to be liquid water, because it tells us in the post that it's liquid, and nitrogen. Ordinarily, with complete combustion, you'd also have CO2. But because and I could add plus Z times CO2, and we find Z is 0 when we do the balance. But just looking at what's coming into the system, I know I'm not going to have CO2 coming out because there's no carbon to form CO2. So you look at each of these terms individually. So for hydrogen, in this case, H2 here, and then there's an H2 there. I know the coefficient in front of this one is 1, so X has to be equal to 1. Then I look at the next molecule. Didn't change the color. Never mind. Okay, so I look at oxygen. So I have an O2 here and an O here. So I know that A theoretical is equal to X over 2. And I previously determined that X was equal to 1 because it balances with this one. So my A theoretical is equal to 0.5. Then I look at nitrogen. So there's a nitrogen here and a nitrogen here. And so I find that A theoretical times 3.76 for this coefficient is equal to Y. I just solved for A theoretical at 0.5, so 0.5 times 3.76 gives me 1.88. So understanding this process is important because every problem in this chapter you have to do it. So in the homework that's homework 10, you'll have to do it too. So make sure that you understand that. We'll do a lot more examples of it, but practicing that and figuring it out is kind of important.
Then where's the 3.76 come from?
The 3.76 N2, this is, this O2 plus 3.76 N2 is just when you're adding air to a system, that's just what it is. It's mostly nitrogen and some oxygen, so that's how it's represented in the equation, is this is the air that you're adding. And your theoretical amount of air, you just multiply A theoretical times that quantity anytime you're combusting with air. If you were combusting with straight oxygen, then you'd have some other number and an O2. But because it's air, it's always O2 plus 3.76 N2. That's just always for combustion with air. So we need to go to our table A26. And so in this energy balance equation, we have a couple of terms. We have our H sub F, which if we look in A26, what is it for H2O2 and N2? The enthalpy of formation for hydrogen, nitrogen, and oxygen.
0.
It's 0 for all of those. Okay, so 0, 0, and 0. That's pretty easy. What is it for liquid water?
Negative 285,830.
Okay, negative 285,830. Okay, in this particular problem, we have H of 298 is our H sub 0, but in the problem statement it says that our products, so this is the temperature of the reactants and the temperature of the products is 298. So those end up canceling out of the equation in this particular one, so it simplifies. We can look these up, but it doesn't matter what those values are because they end up being removed from the equation anyway. Okay, so if we were to write our energy balance equation, so we have negative Q out is equal to the sum of our products times the enthalpy of formation of our products minus the sum of the number of our reactants times the enthalpy of formation of our reactants. Because at 25 degrees Celsius, H is equal to H naught. So that part of the equation here, this will cancel out for each of our terms. That's just because we've said that our reactants and our products are the same temperature. So this part goes away. We only have to worry about the enthalpy of formation, and we only have to worry about the enthalpy of formation for liquid water because everything else has 0 for that value. So if we plug that into our equation, we have negative Q out is equal to 1, which is the number of moles of our product, times the enthalpy of formation, which is negative 285,830 for water, plus 1.88 times the nitrogen, which is 0. Okay, so this is our products. Then we could look at our reactants. It's 1 times a 0 minus a 0.5 times a 0. So this is for the reactants in the system. This is the air, this is the hydrogen, this is the nitrogen, this is the water. So we find our negative Q out is equal to negative 285,830 kilojoules or, let's see, per kilomole. Or in other words, positive Q out is equal to positive 285,830 kilojoules. Okay, so this one is an easy example because it simplifies rapidly. We'll do some more where we have to actually calculate with the additional terms, like this one. Okay, so now we have diesel fuel coming in, And this diesel has a carbon associated with it, C12H26, and it's coming in at 25 degrees Celsius. Burned in a steady flow combustion chamber with 20% excess air. So that means that this air coming in is 1.2 times A theoretical, also entering at 25 degrees C. And the products leave at 500 Kelvin. So we're going to see the difference between products leaving at the same temperature as the reactants versus when the temperature increases. So assuming complete combustion, determine the required mass flow rate of the diesel fuel to supply heat at a rate of 2,000 kilojoules per second. So if we have a Q out dot equals 2,000 kilojoules per second, we have to figure out what is the mass flow rate of our feed. So in order to do that, we're going to need to figure out how much heat this combustion reaction gives off, and then knowing that, we can determine what the mass flow rate should be. Okay, so we're going to balance the combustion equation again. So we have a C12H26, and we're just going to assume 1 kilomole of fuel, plus our 1.2 times A theoretical amount of air, which is O2 plus 3.76 N2. So these are our products. And what would we expect to be the these are our reactants. What would we expect to be the products?
CO2.
Okay, so we have X times CO2 plus a Y times of water plus a Z times nitrogen. Anything else? Because we have excess oxygen coming into our system, we're going to also have some oxygen coming out. So this excess air, this 0.2 A theoretical, is going to show up in our nitrogen. It's also going to show up as 0.2 A theoretical times an O2, okay, because we have extra oxygen. So we start doing this balance. So we balance the numbers here. So we have, for carbon, we have 12 on this side of the equation, and we have X on the other side of the equation. So X is equal to 12. For hydrogen, in the diatomic form, we have 13 on this side of the equation, 13 H2s, and on the other side of the equation we have Y. So Y is equal to 13. We've solved those two. So now we can look at our oxygen. So here we have 1.2 A theoretical times O2 on this side of the equation. On the other side of the equation, we have what? Okay, we have a 0.2 A theoretical. What else?
X on Y.
Okay, we have an X here. And is this Y or is it?
Oh, no, that's, Y is the H2.
Well, the Y is for the H2 and this O. So it's Y over 2. Because we're looking at O2. So this Y over 2 in front of this O is because it's a monatomic oxygen rather than diatomic. So we can solve for A theoretical using our X and Y values, and we find that it's equal to 18.5. So this is 18.5. And then we can solve for our nitrogen. So on this side of the equation, we have 1.2 times 18.5 times 3.76 for nitrogen is equal to our Z value. So we find Z is equal to 83.47. Okay, so again, we've just done the balance. We figured out both sides of the equation, what our molar terms should be for 1 kilomole of fuel. If we input 1 kilomole of fuel, how much air do we need? And then what are the byproducts? Okay, so now we want to find Q. because we know the rate of heat transfer, but we need to find how much total heat transfer is accomplished in this process. So we'll have, again, negative Q out is equal to sum of the number of products, the enthalpy of formation, minus, or plus the enthalpy minus the enthalpy at the reference state. And then the number of reactants, enthalpy of formation, plus the enthalpy minus the enthalpy at the reference state for each of our reactants. So the reactants are on this side of the equation, the products are on this side of the equation. Okay, so we can go to the next slide and give yourselves some room. C12H26, we're going to look up the enthalpy of formation, the reference enthalpy at 298, and also the enthalpy of the products at 500 K. So we need to do that for C12H26, diesel. We need to do it for oxygen, nitrogen, water, and we're going to assume that it's water in the gaseous form because at 500 Kelvin, water is probably not in the liquid form, and then CO2. Okay, so we go to A26 to look up all of the enthalpy of formation values. So for diesel, it's negative 291,010, oxygen is 0, nitrogen is 0, vapor water is negative 241,820, and carbon dioxide is negative 393,520. This is all in kilojoules per kilomole. So then we look up the reference enthalpy for oxygen is 8682 at 298 Kelvin, so we get that from table A19. For nitrogen, it's 8669, that's from table A18. For water, if we're treating it as an ideal gas vapor, it's 9904, that's table A23. And for CO2, 9364, that's table 820. We also look up the values at 500 K using those same tables. So we have 14770, 14581, 14350, 17678. And I didn't leave myself a lot of room here. I don't know why I wrote so big. Okay, so now we start putting that into our equation. So minus Q out is equal to the sum of the products. I'll write it again up here. 9 is equal to the sum of the number of the products, enthalpy of formation, plus enthalpy minus enthalpy at the reference state, minus the sum of the reactants, using those same terms. Okay, so we look at our products, and our equation that we determined was C12H26 plus 18.5 times O2 plus 3.76 N2 on the reactant side is equal to 13 H2O plus 12 CO2 plus 3.7 O2 plus 83.47 N2. Okay, so we look first at products. So we say 13, which is the number of moles of H2O, multiplied by our enthalpy of formation, 241820, plus 14350 minus 9904. Then we look at CO2, so it's plus 12 times negative 393,520 plus 17678 minus 9364. Now we're looking at this O2, 3.7, and the enthalpy of formation for oxygen is 0, so we don't have to worry about that term. But we have a 14770 minus 8682 plus 83.47 times our nitrogen terms, again, 0 for the enthalpy of formation, but we have this 14581 minus 8669. Okay, so this is all the enthalpies for our product. Then we subtract the values for our reactants. So for C12H26, our number of moles is 1. So we multiply by the enthalpy of formation for C12H26 is negative 291,010, plus our H bar minus H naught, but because it's at the same temperature, this is 0. Because it's at 25 degrees as it's coming into the system. Then we can look at our 18.5 times our oxygen terms. So we have a 0 plus a 0, because H minus H bar is 0. It's at 25 degrees Celsius. Then we look at our nitrogen term, which is 18.5 times 3.76 times the enthalpy of formation, which is 0, and these other terms, which is 0. Okay, so the only one we have to worry about on that side of the equation is this. So if we do all that math, we figure out that Q out is equal to 6869110 kilojoules per kilomole of fuel, C12H26. So then if we want to know our mass flow rate of our fuel, our mass flow rate is going to be equal to Q dot over Q multiplied by the molar mass. And the molar mass for C12H26 is equal to 170 kilograms per kilomole. So we do 2,000 kilojoules per second divided by this 6869110 kilojoules per kilomole, and then multiply by the molar mass, which is 170 kilograms per kilomole. So we find our mass flow rate is 0.0495 kilograms per second. Okay, you use this molar mass for our fuel because that's the flow rate that we want to know.
I have a question.
Yes.
Can you go back to the slide? How did you do the part, like, how you solve for the 18.5 and the 83.47?
How did I do that?
Yeah.
It's the same thing that I showed you before. So you look at how many O2s you have on this side of the equation. You look at how many O's you have on the other side of the equation, and you balance all those numbers. So you're creating all of these equations. So here we have these unknowns right now, X, Y, Z, and A theoretical. So you look at this side of the equation, you say, okay, here I have 12 carbons. So if I'm looking at carbon on this side of the equation, I have 12. On the other side of the equation, I have X, and that's it. So I find 12, X is equal to 12. Then I look at hydrogen, and I'm going to look at the diatomic hydrogen because that's how it occurs most often. So on this side of the equation, I have 13 because it's 26 over 2. How many do I have on the other side of the equation?
2.
H2 times,
So,
you have Y in front of this H2. So for H2, you have Y there. If I was looking at just hydrogens, I would have 26 is equal to 2Y, and then I end up finding Y is 13 at the same. So you can you can do it either way, but.
well, I think what I'm confused about is like, for the oxygen, like when you do the balance, you then have like 13 plus 24 plus 0.2. That's what I'm confused about.
What is confusing about that?
Because then you multiply, you only have 18.5.
Well, 18.5 times 1.2 times 2. Because oxygen here is in the diatomic form. Oxygen here is diatomic, here is diatomic, here is single. So this is worth half as much as these other values. It balances out. So if you look at your equation, and I would suggest that this is maybe something you could practice at home, is look at the examples in the book and how they balance things, and see if you can recreate that. Because it is critical to being able to move forward in these problems, to be able to balance both sides of the equation. But I think we need to move on to the new material. So if you have additional questions on that, email me or we can talk about it offline. But look at the examples in the book, look at what we do in class, and then just see if you can balance everything, okay? Okay, so we were just looking at the open system energy balance. So for steady flow system with a combustion chamber where reactants and products come in, or reactants and air come in and products exit, we can also look at chemical reactions that occur in a closed vessel. So for a closed system, there's no mass crossing the boundary of the system, everything is contained, but you can still have a reaction and you can still have a heat transfer to the surroundings, or in some cases, if it's an endothermic reaction, you can have heat transfer to the system. So we can just use what we developed previously. So this part of the equation is the same as for the steady flow system. But if we remember that for a closed system, we have our equation looks like this. Q in plus minus Q out plus work in minus work out is equal to the change in internal energy. And internal energy is related to enthalpy by the pressure times the volume. This should actually be a capital P here. So recognizing that, we can just simply take the equations that we developed for our steady flow system, because enthalpies are easy to look up in these tables, whereas we don't necessarily always have internal energies. And then we just subtract off this PV term. So now we have an additional term in our equation that we have to account for, but that's okay because in most cases, we're dealing with ideal gases, so we can just say PV is equal to RT. And because we're working in the molar form, we use the universal gas constant in all of these. Okay, so it's exactly the same as what we were doing previously, just with one additional term in the equation. So we have to account for the lack of expansion because the volume is fixed in this closed system. If it were a closed system in a piston cylinder device and we actually had boundary work, then we can get rid of this term. It goes away. But we're not looking at that. We're just looking at constant volume processes right now. Okay. So it's important to consider a couple of things. One is that the phase that your fuel is in determines your enthalpy of formation. So if you're dealing with a liquid fuel or a solid fuel or a gaseous fuel, you would use a different enthalpy of formation term than if it was in a different state. And those are tabulated here. This list is by no means comprehensive of every fuel that exists, but there's one that's out there similar to this one. You also need to know the state of the fuel so that you can calculate the enthalpy of the fuel. So enthalpy of formation, in addition to that, you need to know so that you can know whether the ideal gas assumption is valid and if you can just use ideal gas tables or if you have to use a correction factor and maybe you use the ideal gas table to get the initial value, but then you have to use those compressibility tables to find the actual value. So you can see how these problems could get even more complicated as we could add additional layers to it. What's really fun is when we start dealing with humid air. So now we worry about the fuel coming in, but also now we have to worry about that there's some moisture in the fuel as well, and we'll do an example of that today. And that's important because when we cool these combustion byproducts down to low temperatures, some of them may precipitate out. So water might liquefy. We might have water in our products in the liquid form, whereas maybe it was in the vapor form in our reactants. So again, it's a different enthalpy term if it's a liquid versus a vapor. And we also need to know whether the air and the fuel are separate and they're combined as we combust, or if they're mixed together first and then combusted, because it also has a different effect on the entropy calculations, which we'll do on Thursday when we start worrying about how it affects how much energy is available to us by performing these combustion processes. So these are all things that we have to think about and consider. For the most part, we're dealing with ideal gases, and we're even assuming that water vapor, because it's such a small percentage of the air coming in, and it's at a low pressure, we can treat it as an ideal gas in this instance only, these instances only. So for the most part, we're dealing with gases. Occasionally, we have to worry about water that is condensing during this process. Okay, so let's do an example with a closed system. So you can see, I guess, some of the differences in the analysis and the calculations and how you treat those equations. This one's not too bad. So in this case, we have a constant volume tank, which has 120 grams of CH4, which is methane, and 600 grams of oxygen. So we're not combining methane with air, we're combining methane with oxygen. So what would we expect to see in our byproducts?
CO2, water, oxygen.
Yeah, CO2 and water, and in this case, maybe oxygen, maybe not. We're assuming it's complete combustion, so we're assuming all of the oxygen probably is sucked up, but that may not always be the case. You have to sometimes look at that. Okay, so the contents of the tank are ignited and it burns completely, and the final temperature, T final, is equal to 1200 Kelvin. So determine the final pressure in the tank and the heat transfer during the process. Okay, so again, we have to do an energy or a molar balance on these equations, but you'll notice that we're given masses instead of moles. So what do we need to do first with these masses before we approach our equation? Convert them to moles. Okay. So if we were to make a table, we have CH4, O2, H2O, and we're going to assume it's going to be in a gas form at the end of the problem because it's 1200 Kelvin, and CO2. Okay, so we're at the outset going to look up a lot of these property values. So our molar mass for these, if we look at table A1 or A26, or sometimes both, 16 and 32. Yeah, I don't know. We don't have to worry about those because we're only finding the molar numbers for these, and then we use the values to find the others. We don't need to know the anyway. Okay, so the number of moles is equal to the mass divided by the molar mass. So we're going to find it in grams per kilomole, which is fine, because we just need to remember that we did that, so that at the end of our equations, we know that it's joules instead of kilojoules. So in this case, we have 120 grams over 16, which gives us 7.5 moles. Oh no, yeah. Grams per, no, let's see, kilomoles. Oh, that's moles. Okay, 7.5 moles. All right. formation for each of these. For CH4 is negative 74850. For oxygen is 0. For water in the gaseous form is negative 241H20 and negative 393520. So we can look up our H298 from the tables. So table A19, we look up for oxygen is 8682, for water is 9904, and for CO2 is 9364. And this is a value that you'll be looking up a lot. So as you do your homework problems, save yourself some time and just copy it, assuming that you got it correct on the first part. You can just look at your previous problem to see what those enthalpy values are. But these will be distinct, so depending on the temperature of the outlet, this value will change. So H at 1200 K for the oxygen is 38447, 44380, and 53848. And we don't have to worry about it there because those don't come into play. Okay, so our equation is going to be 7.5 CH4 plus 18.7502. And then we have CO2, H2O, and maybe some oxygen. If not, all of it is burnt. Okay, so if we do the balance on this side of the equation, for carbon, we have 7.5 is equal to X. That one's pretty easy. Then we can look at hydrogen. So we have 2 times 7.5, because we're looking at our H2 on this side of the equation, and on the other side of the equation we have just a Y. So Y is equal to 15. And then we look at oxygen, so we have 18.75 on this side of the equation is equal to X plus Y over 2 plus Z. So we sub in X and Y, and we solve for Z is equal to 3.75. So we could rewrite our equation with the coefficients where X is equal to 7.5, Y is equal to 15, and Z is equal to 3.75. So again, if we were to look back at this math, then we can double check, right? So 7.5 carbons on this side, 7.5 on this side. 18.7502s, we have a 7.5 plus 15 over 2, that gives us plus 3.75, gives us 18.75. So it's just a matter of adding everything up and balancing on either side for each of those individual components.
For your chart you have there, for the H2O gas, is there a particular table for that?
A26.
26. And so there's one for...
Yeah, so A26 is where you get all of these H sub F values. For water that you use, there's an ideal gas table for water is A23. Table A23. So we can treat water as an ideal gas. So at the beginning of chapter 15, we sort of looked at that and determined it would be okay to do it if we're in certain temperature ranges or at very low pressures. And because the water is a fairly insignificant component of this whole process, and it's in the vapor form, and it's at a very low pressure because it's partial pressure versus how much space it's taking up. It's low pressure, so we can treat it as an ideal gas. Ordinarily we can't. In a turbine you can't treat water as an ideal gas, even if it's a superheated steam. Here we can because it's mostly air and partly water. Okay, so we want to find the final pressure in the tank. So again, we're assuming this is an ideal gas. So if we look at the pressure of the reactants divided by the pressure of the products, is equal to the number of reactants times the gas constant of the reactants times the temperature of the reactants over the volume of the reactants. And then we can do the same thing for this one, that it's the gas constant times the number of the product, temperature of the product, and then the volume of the product. So if we look at this, our volume is not changing, it's constant. So the volume stays the same. Our gas constant doesn't change. We've already balanced the number of moles on each side of the equation. So the ratio between these two pressures is equal to the ratio between the two temperatures. So we can find the pressure of the products, which will be our final pressure, is equal to the pressure of the reactants multiplied by the temperature of the products over the temperature of the reactants. So this again is just using the ideal gas equation to balance things out. So it's 200 kilopascals. The temperature of the product is 1200. Temperature of the reactants is 298. So we find the final pressure is 805.4 kilopascals. That's part A. So then part B is using our equation, negative Q out is equal to the sum of the number of products. And we have the enthalpy of formation plus the enthalpy minus the enthalpy of the reference state for the products and for the reactants. So it's a lot of subscripts and things to write each time. Okay, so if we were to reference our table and look at our equation, so again we have 7.5 CH4 plus 18.75 O2, 7.5 CO2 plus 15 H2O plus 3.75 O2. And then from our table before, we can look up the values. So for CH4, I don't know. We'll look at the products first. So for CO2, we have 7.5 is the number of moles. Our enthalpy of formation for CO2 is negative 393,520. Plus our enthalpy at 1200 K is 53848. Minus 9364 is our enthalpy of the reference state. Okay, so that's CO2. Plus 15. The enthalpy of formation for H2O in the gas form is negative 241,820 plus 44380, that's the enthalpy at 1200 K, minus 9904, which is the enthalpy at the reference state, plus 3.75 times the enthalpy of formation for H2O, which is 0, plus this 38447 minus 8682. Okay, so that's our products. We now subtract off the reactants. So 7.5 times the enthalpy of formation for CH4, which is at negative 74850, plus the enthalpy at 298 minus the enthalpy at 298, so that's 0. Plus 18.75 times, sorry, this is a closed system. There's additional terms. Okay. Going back to this equation, so these are just the enthalpy terms here. I got sidetracked. We also have to subtract off RU of T for each of those. So here, also minus 8.314 times 1200 K. Minus 8.314 times 1200 K. Minus 8.314 times 1200 K. Okay, inside each of those brackets. So it's 7.5 times this, 15 times this, and 33.75 times this. An alternate way of doing that, if you didn't write it in those brackets, if you forgot and you didn't want to have to erase and rewrite everything, is you could add up all of the moles, so you could do 7.5 plus 15 plus 3.75 times 8.314 times 1200 K, and just subtract it off there. So either subtract it initially or subtract it here. Don't do both. But I just got into my la la land of writing down equations and I forgot this was a closed system. Okay. So also here, we have to consider that term. So minus 8.314 times, instead of 1200 K, it's 298 K, because the products, or the reactants are at 298 K. Okay, so that's 7.5 is the CH4. We now do the 18.75 times O2, which is a 0 for the enthalpy of formation. It's 0 for the enthalpy of 298 minus the enthalpy of 298, but we do have this negative 8.314 times 298 K. So we do all the math on that. We find that Q out is equal to 5251791 joules, or 5252 kilojoules. So I think the hardest part of these is balancing the equation, okay, making sure that you do that correctly. The second hardest part is just keeping track of all of those individual little terms and doing it right in your calculator. So be methodical, be careful, make sure that you can read your own writing. If you have a table in there, it's helpful to help keep things straight. Okay, so now we're going to talk about the adiabatic flame temperature. And as I mentioned at the beginning of lecture, it's if there's no work interaction and our system is adiabatic, so there's no heat escaping, no heat being absorbed from the outside, we don't have any kinetic or potential energies, then these two sides of the equation are equal to one another. So the enthalpies of the products and the enthalpy of the reactants are balanced out. So we have no Q, we have no W, we set those two sides of the equation equal to one another. And the temperature at which this occurs, that these are equal, or the temperature as a result of an adiabatic process, is called the adiabatic flame temperature. And it's not unique because there isn't like an adiabatic flame temperature for any one material, because it depends on whether you're in a liquid or a gaseous state, so what state you're in, how complete the reaction is, and then also the amount of air used. So the adiabatic flame temperature can increase if you use an increasing amount of air, but it can also decrease because perhaps you have an excess of air, and because there's so much air moving through the system, the combustion occurs too quickly, and then therefore it's not complete. So it's not necessarily even a linear relationship, and you have to find the balance so that this adiabatic flame temperature is knowable. In some cases, it's just determined by experiment. In other cases, we have to determine it iteratively, and we'll see an example of that. It's at a maximum when we have complete combustion with the theoretical amount of air and no heat transfer to the outside. So an adiabatic process that's complete with just the right amount of air is going to be the maximum adiabatic flame temperature. And so we don't necessarily know at the outset what the temperature of the products will be, because we don't have a chart of adiabatic flame temperatures. We have to know a lot about the reaction to figure it out. So we have to find it iteratively. And it's important because if our temperature of this combustion process has some certain maximum to it, and we approach that maximum, and the materials within our combustion chamber cannot handle that maximum, then we need to know. So predicting or computing the adiabatic flame temperature is important so that we don't exceed the specifications of our system by going to such a high temperature that it causes a failure. And so all of these things, incomplete combustion, dissociation, heat loss, etc., will decrease the maximum temperature. So if you calculate the theoretical maximum for the adiabatic flame temperature, that's a good upper boundary for you. that there's not going to be something happening in your process unless there's unknown reactants that will cause it to go higher than that. So generally by calculating that temperature, you can be pretty sure that's the maximum it will go, and then you would need to include a safety factor for your materials, that if they're rated up to a certain maximum, really what's the rating, if you include a safety factor. Okay, so let's do an example with octane gas, and we're going to go through this one kind of quickly. So just to see, so you'll have C8H18 plus 30% excess air, so 1.3 A theoretical times O2 plus 3.76 N2. And then in this case, we have 60% relative humidity. And there's a process to go through in order to determine the relative humidity. We don't have full time to do that, but this example is online. And in your homework, you'll need to do it as well. So if you have additional questions on that, then you can ask me, but it's not that hard to figure out. You just have to do an equation. Okay, so so you end up with some amount of H2O, oops, H2O on this side of the equation because there's water within your air. And then you have on the other side of the equation water as a byproduct, CO2 as a byproduct, nitrogen as a byproduct, and oxygen as a byproduct. So if we were to balance this out, I'll just put all these numbers in here. So our A theoretical is equal to 12.5. So let me find my calculation. Okay. So this is 16.25 and O2 plus 3.76 N2. This amount of H2O is 1.48. The amount of H2O on this side is 10.48. CO2 is 8. Nitrogen is 61.1, and oxygen is 3.75. Okay, so that's our balanced equation. So we do this similar process where we look up the enthalpy of formation, we look up the enthalpy at 298, and then we don't have a final temperature to look things up, so we have to figure out an estimate. So if we write this equation in terms of the reactants and the products, so negative Q out is equal to 10.48 times negative 241820, that's the enthalpy of formation for water, plus the enthalpy of water at the exit, which we don't know that value, minus 9904, which is the enthalpy of water at the reference state, plus 8 times negative 393520, plus the enthalpy of CO2, minus 9364, that's the enthalpy at 298 for CO2, plus 61.1 times 0, plus the enthalpy of nitrogen, minus 8669, plus 3.75 times 0, plus the enthalpy of oxygen, minus 8682. Okay, so that's the enthalpy of the products. We subtract off the reactants. And all the values are known for the reactants because the temperature is known coming in. So the reactants, we have 1 times negative 208,450 plus 16.25 times 0, because there's no enthalpy of formation for that oxygen term, plus 1.48 times negative 241820, that's the enthalpy of water vapor, is equal to 0. Okay, because our Q out is equal to 0. So if we set those equal to one another, we come up with a condensed equation that's 10.48 H2O, enthalpy of H2O, plus 8 times the enthalpy of CO2, plus 61.1 times the enthalpy of nitrogen, plus 3.75 times the enthalpy of oxygen is equal to 5857025.4 kilojoules. Okay, so these are all unknowns. We can use ease and we can solve it really easily. Or we can go to the tables. We have to at first come up with some kind of a ballpark figure for where we want to start with our iterative approach. One way to do that is you say, okay, I'm going to take this whole value and divide it by the total number of moles. So if I add up all of these moles, 10.48 plus 8 plus 61.1 plus 3.75, then I find that it's 83.33 kilomoles. So my ballpark enthalpy is 70,287 kilojoules per kilomole. So if I go to my tables and I look at this and I say, okay, most of this is nitrogen. So I look in my tables and I see that at nitrogen, at 70,000 for the enthalpy, that's around 2150 Kelvin. But I know that the enthalpy values for some of these others, like oxygen and hydrogen and others, are higher. So I wouldn't want to start at 2150, I would want to just pick a number lower than that. So just to get something close, I could choose 2000. So you go to the enthalpy at 2000, and you look up the enthalpy of water, the enthalpy of CO2, the enthalpy of nitrogen, and the enthalpy of oxygen at 2000, and you put those values in. Then you say, okay, the value that I came up with doesn't match this, it's higher, so I know my temperature has to be even lower than that. So then you say, okay, I'm gonna guess that it's at 1900. So you go to 1900 and you look up the enthalpy values at 1900 and put those in and you see, and hopefully you'll find a number that's lower. So now you found an upper bound and a lower bound, and you can interpolate in between, assuming a linear relationship, to find what your actual temperature might be. And if you have questions about that, you can look at the example in the lecture notes. Again, it's not that difficult to do. You just have to be careful as you're putting in all of your numbers that you get the right values, because everything depends on you being able to add and subtract correctly in your calculator, and sometimes you put in a plus instead of a minus or whatever happens and it gets messed up. Okay, so that's the last example for today. Your homework's due on Thursday. Get started on the next homework if you want to just have it over and done with and not have to worry about it during Thanksgiving. And then consider doing one of those extra projects if you want extra credit.